So good morning, everyone. Today I have the pleasure to introduce you Professor John Ellis. I will not bore you trying to go through his CV and his extensive career. We will need then 2 seminars, one from me to introduce him and then his seminar, an hour later. I will tell you simply that John is one of the most influential theoretical physicists of the last 40 or 50 years. My personal experience when I arrived at CERN as an undergraduate student to work on my PhD thesis, the theory division, CERN is an experimental place, a very big experimental place with big accelerator, with detectors. But the theory division was kind of the Olympus. So there was this place in a corner of the main building which was extensively considered like sacred land. You would walk there and then you cross Nobel Prizes, and there was some sense of walking into a church or something like that. An exception was the office of John, which was always open and was always full of papers up to the top of the roof, and was always and often full of people discussing physics. For a student like me, it was like, okay, this is what the sacred people in the sacred land do. So my admiration to Professor Ellis comes from a long way. And it was a justified one. He has made major contributions to almost everything that we call theoretical particle physics, ranging from neutrinos, structure of the standard model, quantum, everything. So for me, it's a very great pleasure to give you Professor John Ellis. Thank you very much, John, for being here with us.
Okay, thank you. And thank you very much for the renewed invitation to come to Donosti San Sebastian. I was invited a few years ago, it didn't work out. I'm glad to be here finally. So a few years ago, I was in Saudi Arabia, and I heard a talk about supermassive black holes and the debate that was going on between astrophysicists about how they were performed. And I found this a very interesting problem. And that was one of the reasons why some years later, I got interested in a program in the UK for building atom interferometers, which, as I will describe in my talk, is, I think, an interesting quantum technology which might help us understand the origin of supermassive black holes. I'll describe that later on. And at the end of the talk, I will present some theoretical results related to that. So anyway, that's a sort of very brief outline of my talk. A few months ago, it was a wet Saturday afternoon, and I was getting a bit bored, so I asked ChatGPT to draw 2 merging black holes in the style of Van Gogh. And this is what ChatGPT produced, which I think you will agree is actually pretty good. Oops, hold on. Okay, so I realize this is quite a varied audience. So if you don't mind, I'll start off just with a few minutes talking about where we are with gravitational waves. So, of course, everybody knows that they were proposed by Einstein in 1916. Actually, his original proposal wasn't quite right, but he credited it soon after. Then in 1936, he tried to withdraw his prediction, but he sent it to a journal. The referee said, I think you were right the first time. And Einstein was a bit miffed, but anyway, he changed his prediction. So, of course, the first indirect detection of gravitational waves came with the observation of a binary pulsar by Hulse and Taylor. And he observed two neutron stars spiraling together due to the loss of energy due to the radiation of gravitational waves. Okay, so gravitational waves exist. And they're a new window, which in many respects is unique on astrophysics, cosmology, and black holes. And I'm only going to briefly touch on some aspects of that in this talk. So gravitational waves, which were discovered in 2016, were the mergers of stellar mass black holes. But we believe that there are other sources out there, maybe supernovae, maybe compact objects captured by supermassive black holes, maybe binary supermassive black holes, maybe cosmological gravitational waves generated during inflation or some other mechanism. So up until now, the technique which was used to detect gravitational waves directly was using atom interferometers. There have also been indirect detections using observations of pulsar arrays, and I'll come back to that also later on. But as I said, my personal interest at the moment is in atom interferometers, a new technology which I think is very interesting for elucidating at least some aspects of the gravitational wave spectrum. So I think everybody knows what LIGO and Virgo look like. Here are a couple of pictures of the LIGO detectors. I believe some of you are actually working on LIGO. And here, not ChatGPT this time, is a simulation of the merger of a pair of black holes. So there's various different stages in the process. You start off with an in-spiral of the two objects, like the in-spiral of two pulsars, which was observed by Hulse and Taylor. And then they merge, and then they form initially some sort of a dumbbell, and that dumbbell sort of shakes down in the so-called ring-down process. And here is the waveform which was observed by LIGO of the first such binary solar mass black hole merger. So subsequently, many other black hole mergers have been observed. This is not a complete catalog, but this just gives you some impression. So there's been observations of not just mergers of pairs of black holes, but also pairs of neutron stars with black holes. So you'll notice that the maximum mass here of the black hole observed is around 100 solar masses. And that's potentially because of two reasons. One reason is an instrumental limitation, that if you want to observe higher mass black hole mergers, you need to go to lower frequencies beyond the reach of LIGO and Virgo. But of course, it's also possible that higher mass black holes don't exist. Well, actually, just recently, there has been one observation of the merger of a pair of slightly more massive black holes. So this particular pair weighs around 100 solar masses or more. there's still an open question, whether there are heavier black holes out there whose mergers we could potentially observe. And that's where I believe that atom interferometers have a role to play. Now, of course, we do know that there are supermassive black holes in the centers of many, if not most, galaxies. And this is the first image that was made by the Event Horizon Telescope of the surroundings of the black hole in the center of the M87 galaxy. So that weighs a few billion solar masses. The Event Horizon Telescope has also provided an image of the black hole in the center of our own galaxy, which weighs a few million solar masses. So those are supermassive black holes. The question is still open whether there are mergers of black holes intermediate in mass between what LIGO and Virgo have observed and the masses of these supermassive black holes. So that question provides much of the motivation for the LISA spaceborne atom interferometer, which is currently under construction. So they hope to observe mergers involving supermassive black holes and maybe lighter black holes, or maybe detect mergers of supermassive black holes themselves. And that will come into operation in about a decade from now. So this picture here illustrates the sensitivity of LISA. So it's optimized to detect gravitational waves with a frequency around 10 to the minus 2 hertz. Just for the record, LIGO, Virgo, and Kagra are optimized to detect frequencies around 100 hertz, so somewhere off the right-hand side of this picture. So LISA would be able to observe, if they exist, mergers of objects weighing maybe 1 million solar masses. LIGO, Virgo, Kagra up to 100 solar masses. If you want to observe mergers of objects with intermediate masses, you need to go into a region around 1 hertz where LISA loses sensitivity and where LIGO, Virgo, Kagra cannot actually see directly the mergers. So this gap in the frequency range, LIGO, Virgo, Kagra on the right-hand side, LISA in the middle here, and there's a gap in between. And what you might hope to observe in that intermediate frequency range is mergers of intermediate mass black holes, which could play a role in the assembly of supermassive black holes. Presumably, there's a sort of complicated hierarchical process where black holes merge and black holes merge and black holes merge until eventually you get a supermassive black hole. But in order to cast light on that, you would like a detector in this range over here. So I should also mention pulsar timing arrays. So there are various groups around the world that look at the perturbations in the signals arriving from pulsars, which are generated by the passage between us and the pulsar of a gravitational wave. And as I'll discuss in just a moment, these are sensitive at a very different frequency range, around the nanohertz range. But the observations by the pulsar timing arrays indicate that there are indeed out there binary systems containing supermassive black holes in a very early stage of infant. Okay, so now I come back to Saudi Arabia. So I had a talk there about mechanisms for making supermassive black holes. And what I remember from the talk was that there were different hypotheses. So one hypothesis was that you started off with light seeds, maybe the relics of population 3 star, early generation of stars, weighing perhaps 1,000 solar masses. And then you start putting all those light seeds together until eventually, like a pomegranate, you get a supermassive black hole. An alternative hypothesis was that you have like primordial halos of galaxies which collapse spontaneously to produce heavier black holes, not supermassive, but intermediate mass black holes weighing, let's say, of the order of 100,000 solar masses. And then either coming down this route or coming down this route, you would go through a process of mergers and accretion, which would eventually produce those supermassive black holes. So as I said, I got interested in this problem. And so what can we say about the possible existence of intermediate mass black holes? So until recently, there was not really extremely solid evidence for the existence of intermediate mass black holes weighing, say, 10,000 solar masses. But one recent observation which caught my eye was in our own Milky Way, not so far away, there was evidence for an intermediate mass black hole weighing several thousand solar masses. And unfortunately, in this image, it doesn't show up very well, but the way in which this was detected was by looking at the proper motions of stars in the constellation Omega Centauri. And if you look very carefully here, you can see little arrows, and those little arrows tell you how fast those stars are moving, and then you can infer from that the gravitational field, and you can tell that there was a black hole there weighing several thousand solar masses. So individual intermediate mass black holes certainly exist. The question is, how often do they merge, and what is their role in the assembly of supermassive black holes? So this image here shows you what light LISA and next generation of solar mass black hole experiments might be able to cast on that. So the horizontal axis is your black hole mass. So the Einstein telescope, which is proposed as a successor to LIGO and Virgo, could observe in this frequency range here, corresponding to masses maybe 10 to the 2, maybe 10 to the 3. LISA could observe mergers in a different frequency range corresponding to heavier black holes. But there is a gap in between, and as you can see here, this is a simulation done by the Einstein telescope people, they would miss a whole bunch of these mergers, which would be key for understanding how you make a supermassive black hole. Okay. So that was my motivation, one of my motivations, for getting you interested in the idea of using atom interferometers as quantum sensors to look for the mergers of intermediate mass black holes. So LIGO, Virgo, LISA, they are a classic laser interferometer. You start off with an input laser beam, you split it, you have mirrors, you bring the beams back together again, and you look for an interference pattern. So how do you interfere atoms? Well, you start off with a cloud of cold atoms. You manipulate them with a laser beam. A first laser pulse separates the cloud into two parts. The second pulse acts as a mirror, bringing those two parts of the cloud back together again. And when the two parts of the cloud come back together again, you look at the interference pattern. Principle is very similar to a laser interferometer. We're just using shells of cold atoms. So perhaps I should have explained here. The two parts of the cloud are separated. They're separated because when you bombard them with a laser, you hit some atoms, but not others. And the ones that you hit move away. Because when you give them energy, you also give them momentum. And then you bring them back together again. And so the fact that you've got these clouds separated means that you're sensitive to the passage of a gravitational wave. In the same way that in LIGO and Virgo, you've got laser beams following separate paths, and the separation between the paths gives you sensitive to the passage of a gravitational wave. Okay, so that's the basic idea. And I got involved a few years ago in a collaboration in the UK, which brought together various different laser groups in different universities, and my group at King's College London acting as the sort of theorists behind this experimental collaboration. So I might mention that we in the UK, it's called the AON collaboration, work very closely together with a similar collaboration in the United States called MAGIS. And eventually we would hope to have two different detectors in different parts of the world, one in the US, one in Europe. And then by comparing the signals from the two, we would have a network rather like LIGO and Virgo. But that's, for the moment, still in the future. So at the moment, we're still at the laser laboratory stage. We would hope, once we've demonstrated successfully the atom interferometry technology, we would hope to be able to build a 10-meter device. And we got initial funding from that, from the UK funding agency. Then we would progress to build a 100-meter device, a kilometer-length device, and eventually we would like to go into space. You know, that's I'll probably be in my second century by the time that happens. So what would such an atom interferometry device actually look like? So what you do is you launch the atoms in a vertical vacuum tube, and then you manipulate them with lasers in the way that I described. They go up, they come down, but they follow different trajectories. So that gives you your sensitivity to a gravitational wave. But there's other phenomena which could also have a similar effect on your atoms. So what you would like is to have several interferometers all arranged along a vertical shaft. And as I said, that vertical shaft might be initially 10 meters, then 100 meters. So I've emphasized my personal motivation in this type of quantum sensor, namely gravitational waves. But there are other things that you could do with them. And one of them is you can probe the possible existence of waves or clouds of ultralight bosonic dark matter. And this is a picture showing what those waves of ultralight dark matter density might look like. The wavelength of those waves depends on the mass of the boson that forms the cloud. If, for example, the mass is about 10 to the minus 15 electron volts, then the wavelength would be comparable to the distance between the Earth and the Sun. Now, the basic idea here is that if that ultralight dark matter field interacts with the constituents of an atom, then it affects the energy levels inside the atom. And that energy level shift then affects the interference pattern that you get in your atom interferometer. So here is the effect on the phase which we get from this shift in the energy of the excited atom, which comes from the manipulation with the laser. So I regard looking for ultralight dark matter as in some sense being an entry-level objective for the sort of atom interferometer that I'm describing. I call it entry-level because even with a relatively small detector, you start being sensitive to the interactions of ultralight dark matter with atomic constituents, which goes beyond the present experimental limits. So if you're lucky, already a 10-meter device goes beyond the current limits, and with 100 meters, you go well beyond, and so on and so on. So realistically, when you switch on an atom interferometer, I don't expect to see gravitational waves for a while, should we say. But ultralight dark matter might possibly show up earlier. Okay, so my colleagues in the UK have been busy developing the technology that you need to build such an atom interferometer. And these are pictures of some of the laser laboratories that are dotted around the UK. This is an illustration of where we proposed to install a 10-meter entry-level experiment. So the Oxford Physics Department has a wonderful basement. It goes down very deep. It's seismologically very stable. It has a nice room at the bottom where you could install a laser laboratory. And so we've done a detailed engineering study of what such a 10-meter device would look like. And we're currently awaiting a funding call from the UK funding agency where we would apply to actually build this device. How about a 100-meter device? So there's not so many places where there are vertical shafts where you could put your atom interferometer vacuum tube 100 meters long. One place where there's plenty of beautiful vertical shafts is CERN. So we've identified one location around the LHC ring where there is a vertical shaft which provides access, which is not used very often. And we've been discussing with the CERN engineers whether we could conceivably install an atom interferometer. And they say, yeah, sure. We just put it against the wall over here. And the apparatus is like a couple of meters across. This vertical access shaft is like 10 meters across. there's plenty of room to put such an atom interferometer in this CERN access shaft. And following the studies made in conjunction with the CERN engineers, we have just a couple of months ago submitted a letter of intent. Excuse me. Well, frog in my throat. It's not a disease, it's just a frog.
Yeah, there's
So
more water there if you.
Yeah, maybe I'll do it. So we've submitted a letter of intent to the CERN management for such a detector, which we call ACE, Atom Interferometer CERN Experiment. And there's a number of groups in particle physics and cold atom technology around Europe who have joined the prospective collaboration. And we're now waiting to hear from the CERN management whether they would be interested in supporting such an experiment. Okay, so we found a 100-meter vertical shaft. Actually, it's 140 meters. But how about a kilometer vertical shaft? Well, we don't have any of those at CERN. But a few years ago, I went to give a talk in Ticino in the south of Switzerland. And to get there, you go through the Gotthard railway tunnel, which goes about a kilometer underneath the Alps. And shortly afterwards, I was in the CERN cafeteria, and it occurred to me there must be some sort of vertical shaft going down to that railway tunnel. Quick Google search, yes. Actually, there's a pair of shafts, which are about 800 meters long, and they would be possibly a site where you could put an atom interferometer. So a year ago, we visited the site with the guests of the Swiss railway company, and the railway engineers that we met were very helpful. They allowed us to do seismological studies, and they seemed to be interested in the possibility of hosting such a large interferometer. Of course, it's one thing if the engineers are interested. It's another thing if the management is interested. So we'll see. So I should also mention that there are other groups around the world who are interested in developing atom interferometers. So there's a group in Germany. There's a group in the US that I already mentioned. There's a group in France, and there's a group in China. And we actually have a sort of proto-collaboration where we talk between all these groups to try to see how we can put it together to advance this technology. Okay. So here is what you might call the money plot. So over on the right, we have the sensitivity of LIGO, which is best around 100 hertz. And here on the left, we have LISA, maximum sensitivity about 10 to the minus 2 hertz. Here is the gap in between, around 1 hertz. And here are the prospective sensitivities, 100-meter and kilometer length detectors, also possible spaceborne detector. And so what you see is that AON 100 could maybe already see the merger of intermediate mass black holes weighing 10,000 solar masses. AON 1 kilometer could see further out to larger redshifts. You can also see that atom interferometers could prospectively measure the infall stages of mergers that would subsequently be seen by LIGO and Virgo. And so there's synergies between atom interferometers and laser interferometers. Okay. So in principle, you can imagine observing mergers of intermediate mass black holes. But in practice, do you actually expect to see mergers of intermediate mass black holes? So the next part of the story that I'd like to introduce is pulsar timing arrays. So as I mentioned in the introduction, what they do is they look at the signals coming from pulsars in different directions in our galaxy. Emissions by those pulsars are incredibly regular, but if a gravitational wave passes by, it perturbs the arrival time of the gravitational wave. And those perturbations have apparently been observed. So these are data for one particular pulsar timing array called Nanograv in North America. And they see a signal which is above the pulsar noise. That signal shows a correlation between the perturbations of signals from pulsars in different angular directions. And there's a characteristic prediction for that, which comes from the spin-2 nature of the gravitational wave. And that Hillings-Downs angular correlation is apparently detected. If those gravitational waves are due to infall of supermassive black hole binaries, then you expect a characteristic spectral index in the signal. The data don't agree perfectly with that, but they're not inconsistent with that either. So we got interested a while back in trying to understand that pulsar timing array signal. And here I would like to introduce Juan Urrutia, who is originally from Donosti San Sebastian, who is a student that we're working with. Very good student. Give him a job. Just saying. Okay, so we constructed a model for the formation of black hole binary systems based on a standard formalism for the mergers of galactic halos, or the extended Press-Schefter formalism. And then we assume that when these halos come together, eventually the black holes in the center of them merge, and then you try to calculate what the pulsar timing array signal would be. So this plot shows some results. So just to orient you, we're here in the nanohertz range, so 10 to the minus 9 hertz. So the time scales for these binaries are years. Okay? The vertical axis is the strength of the gravitational wave signal. So the sort of orange shapes here, called violins, represent the measured signal. Of course, you're not absolutely sure how strong the signal is, and so you get a sort of fat shape. The fatness tells you how likely that particular amplitude is, according to their data. And then the blue and the green violins are simulations, and you get a pretty good fit, assuming that these binary systems are just losing energy through gravitational wave emission. that's the blue violins. But you get a better fit if you allow for the possibility that there are additional energy losses coming presumably from the interaction of those black holes with the halos in which they're embedded. So for the moment, this is somewhat preliminary. This is the best we're able to do with the data. It was published a couple of years ago, but we look forward to more data shortly. Okay, so these pulsar timing array observations, here are their violins again, and these different lines correspond to different models of the gravitational waves that they're apparently observing. So the band here is supermassive black holes, which is, if you like, the default favored astrophysical interpretation. But now you can also model the pulsar timing array data using models based on particle physics and cosmology. And those are shown by these lines here. Phase transition, domain walls, etc. So those particle physics models actually fit the data a little bit better than the default astrophysical model, but not so much better that you should abandon astrophysics. And as I said, we're looking forward to more data in the future to see whether we get better discrimination between astrophysical and cosmological models. Now, what I also show on this plot is an extrapolation, assuming that we're looking at binary supermassive black holes. And this fixes, if you like, the overall normalization for mergers of black holes at different frequencies and different masses. And you see that the signal should be observable in LISA, should be observable at a interferometer, at least if you've got a 1 kilometer length at an interferometer. So, according to this scenario, you should be able to observe such mergers of intermediate mass black holes. So how am I? Well, I'm pretty much out of time. I should particularly run through this. So in the last couple of years, there have been a lot of observations of supermassive black holes in the early universe with JWST. And a lot of astrophysicists were kind of surprised that there were so many of them. In our model, we're not so surprised. We find that the number of supermassive black holes observed by JWST is, roughly speaking, consistent with the number of supermassive black hole binaries that you would need in order to explain pulsar timing array data. And so we did a global fit, which within all the stochastic uncertainties seems to fit the available data. And here again is this comparison between our violins and the observational violins. And this makes the point that, at least in our model, you can understand simultaneously the JWST observations and pulsar timing array data. So finally, let's come back to Saudi Arabia. So, are those supermassive black holes being made by light seeds or by heavier seeds? And so these are some fits that we did to data from JWST, from other data on high redshift quasars, and local AGNs and local inactive galaxies. So are light seeds or heavier seeds preferred? And the answer is there's no clear preference. JWST has maybe a slight preference for lighter seeds, but I think realistically you cannot discriminate between light seeds, population 3 star remnants, and heavier seeds, remnants of primordial haze. And this picture somehow illustrates why. So here we have a couple of sample simulations. One starting off with heavier seeds weighing about 10 to the 5 solar masses, and one with lighter seeds weighing about 100 solar masses. And what we find in our simulations is that the light seeds catch up quite quickly with the heavier seeds. And so it's difficult to distinguish between them with observations at a redshift of 10 or less. But I draw your attention to something else in this picture. So the solid lines are when we do simulations with conventional cold dark matter. Doesn't matter whether that cold dark matter is particulate heavy particles or whether it's waves of ultralight dark matter. But if you make your ultralight dark matter too light, then you no longer fit the data. And that's illustrated by these dashed lines where we postulate super ultralight dark matter weighing about, whoops, not 10 to the plus 20, that's 10 to the minus 20 electrons. If that's the only misprint on my slides, I'm not doing so bad. So you can see that measurements at a redshift of the order of 5 to 10, which is where you got data from JWST, could potentially discriminate between this super ultralight, so-called fuzzy dark matter, and cold dark matter. So the reason for that is that if you make your light dark matter too light, then you cannot form small halos. And those small halos play a role in the assembly of your supermassive black holes at high redshifts. And these plots here show you how the mass of, I got the sign right this time, from very light, so-called fuzzy dark matter, you get a cutoff in the halo size, and that would impact your mechanism for generating supermassive black holes. So I talked about fuzzy dark matter, which is ultralight, light dark matter. But there's a similar effect in so-called warm dark matter, where instead of postulating an extremely heavy particulate dark matter candidate, you postulate something which is of the order of a keV. So potentially, these simulations that we do, the assembly of supermassive black holes, could be sensitive to the masses of dark matter candidates. And this picture here illustrates a comparison between the data and simulations assuming, for example, fuzzy dark matter. And you can see this particular pair of simulations. The fuzzy dark matter does not fit as well as the cold dark matter. So potentially, you get a constraint on the nature of dark matter. And so that previous plot was assuming light seeds, where there's a big effect. If you have heavier seeds, not such a big effect, but there still is an effect. So this taken from our most recent paper is a pair of money plots which show you the constraint that you get on the nature of dark matter from this modeling of supermassive black hole assembly. So you get a lower limit on the mass of ultralight fuzzy dark matter, and you get a lower limit on the nature of warm particulate dark matter. So these limits are comparable in strength to other constraints that people have derived from different astrophysical considerations. But it's a novel type of constraint, completely different approach, and we think this is potentially interesting for the future as the data improve. Okay, but I'm supposed to be talking about gravitational waves. So finally, I want to describe some work in progress where we analyze how gravitational wave experiments could potentially discriminate between different types of dark matter modeling. So here again is this plot where I compare the supermassive black hole spectrum that you get with cold dark matter and with light fuzzy dark matter. And you see, well, the fuzzy dark matter predicts less black holes, presumably also less binary black holes. So over on the right-hand side, I show a simulation that we did showing the number of intermediate mass black hole mergers that you might hope to observe with a 1 kilometer atom interferometer and light seeds. So lots and lots and lots of events. So you could observe a lot of events with an atom interferometer if the seeds are light. If the seeds are heavier, LISA would do better. And these dashed lines show what happens if you postulate fuzzy dark matter around the current limit that we derived. And you see that you get a lot less events, but still plenty to detect with either an atom interferometer or LISA. So, atom interferometers are potentially capable of detecting mergers of intermediate mass black holes, and those observations could potentially constrain models of dark matter. Okay, so that's the end of what I wanted to say. Gravitational waves have provided a new window on astrophysical black holes. Atom interferometer technique fills the gap between LIGO, Virgo, and LISA. There's projects in the UK and elsewhere to develop that technology. It could detect the intermediate mass black holes, which would play a role in assembling supermassive black holes, and observations of those mergers could potentially constrain the nature of dark matter. Thank you.
I have many. Let's start from the end. Thank you, first of all. So from the last things you mentioned, I was actually wondering, So you took the case of having either light or heavy seeds, and then fuzzy dark matter or cold dark matter, right? And showing the differences and how you could
Yeah.
distinguish between the two, both with the JWST, but also the population of high redshift black holes, but also with the gravitational waves. I was wondering which are the other parameters that they are very degenerate with. So for example, the growth mode of black holes. If they're growing at super Eddington, we are doing similar models and we find a lot of degeneracy with the modes of growth.
Right. So I would not claim to have done an extensive survey of all the possible models. I might mention that the model that we constructed is constrained from observations of UV light from JWST. And this is a constraint that we impose on our model. We've got a separate paper about that, which I didn't have time to discuss. But maybe that would be interesting to you. I mean, clearly one of the degeneracies is in the masses of the seed black holes that you assume. Are they all light? Are they all heavy? Or is there some mixture? Presumably there is some sort of range of masses. But I think what we would argue is a combination of atom interferometer and LISA data would be useful because you get a much bigger effect, for example, for heavier seeds with LISA than with AON. And you can also see that the shape of the spectra depends on the nature of your dark matter. So we haven't done exhaustive studies, but I think that what we've done is indicate that there is something interesting here, which we think is deserving of future study.
Thank you. Can I ask another one? Yeah, well, yeah. Yeah. I go for another one. I was actually curious, so I think I missed it. What's the dependence of the frequency of detection, where you have the highest, so the down of the curve, or the highest sensitivity, with the size of the interferometer that you have from 1 kilometer to, from 10 meters, I think was the minimum, to 1 kilometer, only affects the sensitivity, but not the frequency, correct?
Correct.
Whereas the laser interferometer, the size is actually affecting the frequency, not the sensitivity, right? So I was wondering what is giving the peak at 0.1 Hertz? I think I missed it from your description of the atom interferometers.
Okay. Well, first of all, I would comment that size is important whether you're talking about a laser interferometer or an atom interferometer. For both the sensitivity at a fixed frequency and also the frequency range that you can cover. So, for example, the Einstein telescope is projected to reach down to somewhat lower frequencies than light. But there is a limitation in all these ground-based laser interferometers, which is due to a gravity gradient noise, which, if I understand correctly, is basically the shaking of your mirrors. And that is a limitation which you overcome with an atom interferometer. You still get some sensitivity to seismic waves, the so-called gravity gradient noise, but you can get down to a lower frequency. So this is something which we've tried to evaluate for the CERN site and also a first stab at the Gotthard railway tunnel site. But this is something which is still under study. What you do see is that for an atom interferometer, as for a laser interferometer, you gain in sensitivity by having a bigger detector, but you also gain in frequency coverage.
But sorry, why is it point, like, why is the peak between, what sets the 0.1 to 1 hertz frequency?
So that's a combination of different factors. I'm
Okay,
not going to be able to tell you the details of that, but there's things like the shot noise, which depends on how many atoms you have. There's the laser noise. So all these things have been taken into account.
okay. Mhm. Thanks.
Okay,
Sorry, thank you for the great talk. Can we go back to the testing, the fuzzy diameter and the CDM case? So, what was the black hole formation channel you assume? Are they assumed to be the same? So you consider the merger of the halos dominantly.
So what you see here are results for, in blue, heavy seeds,
Yep.
in orange, light seeds, solid lines, cold dark matter, and dotted lines, dashed lines, are the fuzzy dark matter. We considered the four different possibilities.
Right. The key question I probably want to ask is for fuzzy diameter, they have a solitone core in the center, and that may speed up the merging of the light seeds. Is that considered as well, or also the solitons themselves, if they get dense enough, they can, I don't know if they can collapse into supermassive black hole? And
So
do you see?
we didn't consider that.
I see.
go ahead.
So, how does an atom interact with this ultralight dark matter field? So you had this figure where you have these energy levels that are modulated in time. Is it like gonna take this literally, or is it just? I mean, what is known about this?
Okay. So in many ultralight dark matter models, there's some sort of an interaction with regular matter. Okay. And that some sort of an interaction has to be with constituents of atoms. So here you see potential interactions with electrons, with gluons, and with quarks. So what you do when you're manipulating these clouds of atoms is that you excite some fraction of the cloud. But the energy level could potentially be affected by that interaction with any of these atomic constituents.
So this is electromagnetic interactions.
Well, you could also consider direct interactions with quarks, for example, or direct interactions with gluons, which are all constituents of atoms.
So is this kind of actually a model coming motivated from the QCD strong problem, or strong CPU problem, or they have a separate model motivated for this kind of?
In this particular study that I show here, we consider scalar ultralight dark matter.
Yeah.
Whereas the axion, of course, is pseudoscalar. So you can get sensitivity to pseudoscalars by using different isotopes of the same atom. So I didn't mention which specific atom we propose using. We're proposing to use strontium. It's got a couple of nice isotopes which you could use to look for pseudoscalar type dark matter. Other groups are considering other possible cold atoms.
More questions? Go.
Thanks for the talk. So with this action atomic interferometers, you are sensitive, I guess, to an average signal, right? So is there a possibility at some point to have more localization of where this a particular signal might come from?
So the signal could be modulated on quite long time scales. So the Earth rotates, the Earth orbits, so that already gives you some sensitivity. Also, of course, if we could establish a network with, 2 or more detectors, then that would also give you some sensitivity.
So I guess this would be super cool. Huh?
And of course, having a network would also reassure you that, for example, if you're observing gravitational waves, that you can tell what direction they're coming from and so on.
So roughly what type of spatial accuracy would you have? If you have, like, for instance, these 5 or so experiments that you mentioned?
Well, so we haven't done detailed simulations of a network because at the moment these are all paper projects. Right? What I have actually done, which is closest to what you're interested in, is if you have one atom interferometer, then, and supposing you see a signal which would correspond to infall of a LIGO-Virgo type black hole merger. We've done calculations of how sensitive you would be to the masses, the time of the final merger, and the direction. And just the fact that the time scale of the infall is relatively long, and the motion of the Earth gives you sensitivity to mass, redshift, and time scale. And wrote a paper a few years ago where we analyzed that. But more detailed studies of a network, that's for the future, I think.
Thank you.
Was there a question around there? No more questions? Yeah, go ahead.
I have a really simple one. Maybe I missed it out. I'm sorry. Why the vertical shaft? That's the orientation of a...
So thank you for that question, but just I realized something I didn't fully explain. So in a vertical shaft, you can launch your cold atoms at various different heights. And you compare the signal between the atoms here and there. And this is a way of suppressing backgrounds. In particular, there's noise in the laser beam, which is being used to manipulate the cold atoms. And that laser noise you would like to cancel out as far as possible. And my experimental colleagues at Imperial College have done a first experimental study of this. So they launch a pair of atom clouds, and they compare the signals in the two, and they subtract them, and that gets rid of the laser noise. So that sounds very exciting, but I should say that the separation between the clouds is infinitesimal. It's less than a centimeter. Okay, but it illustrates the principle that by manipulating simultaneously many clouds arranged along a vertical axis, you can suppress the noise associated with your laser and also noise coming from seismic vibrations.
Okay, so let's thank John again for this talk.
I have one more question. Yes, so would you also consider fixing that mix that matter model as possible? Like there is, say, a fraction of that method, and then fraction of the quality that matter or whatever.
Yeah,
That's entirely possible.
Because I read that the motivation for positive matter is coming from string activity. And also some kind of velocity, strong CP.
I think the thing, guys, I can't tell you what the mass is.
That's for yes.
You do suggest there might be various different contributors to the discussion. So that against them. That's a whole different.
Oh, yeah, right. Because, yeah, one thing about that is that I don't fully understand is if they predict with the strings, perspective, if they predict ultralight kind of axioms. And there are some electronic particles associated, partners associated with the axioms, I presume. How do you get rid of those?
So the experiments which I described in detail will be sensitive to dilaton-like particles. If you want to look for axion-like particles, you would want to look at different isotopes. But this is something which we also do in the same apparatus. A different experiment using the same rates.
Okay, so the dilaton they also be very light as well. I see.
Isn't it that? It's not.
I mean,
Next up. Yeah, so we have a reservation now for lunch.
Maybe we just give you a few minutes to.
I think people went to pick up their jackets, so I will be here.
That's why you love it. Thank you. I have been admiring your works on the PTA black holes.
Right.
I wanted to ask about this gamma that is
Yeah.
modified by the environment.
Right.
Are there any thoughts on what could be the main driver of this environment, or who can constrain that with your models as well, right?
Okay. So in one of our papers, we had some remarks about that. So you've got various different sort of environmental interactions that people considered. So some of them, if you like, accelerate the very, very early stages of infall. What you're actually observing is the last stage, which is taking place over years.
Yes.
Because the maximum period of time that people have studied is 10, 15 years. And there, I have to say, we don't have a model for that. What we can say is that the data seem to prefer some sort of environmental effect.
Yeah, but I had in mind, because we study massive black holes, like here with Sylvia's group.
Yeah.
About like gas, circumbinary disks, or like a scatter of stars.
Exactly. These are amongst the mechanisms.
So there's no way to say, this gamma, of course, with this data, it's difficult to tell if there's deviation from gravitational-only mergers. But my point is, if we are hoping to find a clear signal, when we have a clear signal, if we can tell something about, okay, it's the circumbinary disk that drive the black hole.
Yeah.
If you have any thoughts,
Maybe we can just sit down for a second and I will try to find where we studied that.
okay.
Unless we. Raul, when is the reservation?
Sorry?
When is the reservation?
Okay, so maybe you would like to,
I think they're waiting us for lunch.
yes,
They're waiting us for lunch, otherwise we'll be late. But we can check with,
I think I can,
Let me see whether I can do this in 1 minute.
okay.
I don't want to keep people waiting, but
No, more for you because you said you need to leave by 3, right?
yes. I mean, I can find, I'm aware of how this works.
Tono de la región con.
So my point I would like to make is that, we observe through light many, or we wish to observe many binaries. So maybe like a combined.
yeah. Maybe this is a paper. No, it's not that big. Okay. I don't find it.
No way, I can. But if you like say that you talk in your paper about that, I can
Yeah, we can check
definitely
again.
take it.
Yeah, okay.
Thank-
Yeah, but that's the difficulty. There are so many degeneracies with also other things.
Right.
It's hard to really see what is, I mean, you find the environment is giving you a specific signal on the
Yeah.
frequency dependence.
But the different types of environmental effects that people talk about are most important at different distances and hence different frequencies.
Yes.
Yeah.
And we have a very nice plot in one of our papers where we sort of illustrate that.
But also in these long periods, these low frequencies, we also have some possible indications of periodic modulations. So,
Pen?
but my point is that if it's just something that we can compare with others, and if you
Um,